This is the lecture on this is the lecture on fiber reinforced polymer composites as part of the course on modern construction materials. And we have already discussed polymers. Now we will see what happens when these polymers are reinforced with fibers to give us a composite that is very strong and reasonably ductile as well. We will look basically at applications that involve strengthening and retrofitting of structures. On the leader slide here I have a photo of a concrete slab. This was part of a house where a wall had to be removed, and what was done is there are carbon fiber polymer laminates. These are the laminates strengthening the slab, and the ends of these laminates are held together by this carbon fiber sheet that is also glued on to the slab. So this system as such was used to strengthen this concrete slab at IIT Madras. Now what is a composite? We have talked several times about composites. A composite is a combination of two or more materials which are different in form or composition on the macro scale. That is, when we see them we can clearly identify that these are two different materials, and in the composite the components or the constituents of the composite retain their identities. That is, they retain their properties, they do not dissolve or merge into each other, although they act together. There is a composite action, but each of them behaves differently in terms of the constitutive behavior as opposed to what would happen say in an alloy. And normally when you see the components they can be physically identified, you know that the components are different, and there is also a significant interface between the two components. So that is, the interface is very important. There is a clear interface between the two components. There is a clear interface between the two components. Fiber reinforced polymers are composites that consist of high performance fibers embedded in a polymer matrix, and these fibers are generally carbon and glass and to some extent aramid, but we will see that mostly it will be carbon and glass. Fiber reinforced composites can have different systems of fibers within the polymer. You can have a one dimensional arrangement where all the fibers are in one direction. Lot of the fiber reinforced composites that we have in civil engineering applications are of this type. You can also have a random arrangement. This happens sometimes in boards that are used for maybe non-structural applications. So you have a two dimensional arrangement, but it is a random arrangement of fibers, or you can have a mesh. This to some extent again we use in reinforcement systems in strengthening and retrofitting. So here you have a mesh or a grid of fibers within the polymer matrix. This is two dimensional, and in some cases you can have a totally random arrangement like what you see here. So the most common systems that we use are the one dimensional arrangement and in some cases the two dimensional arrangement of fibers within the polymer matrix. What is the function of the polymer? As the name implies, a fiber reinforced polymer means that there is a polymer matrix and fibers embedded inside. The function of the polymer is basically to hold the composite together. The function of the composite is to transfer, the function of the polymer in the composite is to transfer stress between the fibers, because the fibers are separated from each other. The polymer transfers the stress from one fiber to the other and also gives the composite a certain shape. It protects the fibers also from mechanical and environmental damage and basically holds the composite together. Some of the common polymers used in structural composites are given in this table: polyester, vinyl ester, epoxy and phenolic resins. The densities you see are not very high, quite low density. This is one of the advantages of FRP composites in structural applications. The weight or the density is not very high. So, we can get a significant strengthening without increasing the weight of the structure. The tensile strength is reasonably high of the polymers compared to say what we would have in a brittle material such as concrete, which typically is reinforced with such FRPs. Elongation is quite high in the order of 1 to 8% elongation. The modulus of elasticity is low as we are just considering now the polymer, in the order of 3 to 4 gigapascals. What about the fibers? We have a range of fibers that can be used, but we use very few of them in the reinforcement applications or strengthening applications. We will look later at how steel fibers can be used in concrete itself. Now, most of the applications that we have in terms of strengthening and retrofitting look at or consider 3 fibers: glass, carbon and to a limited extent aramid or Kevlar fibers. So, I have marked here highlighted here the properties of these fibers. Glass fibers are thin in the order of 9 to 15 microns in diameter. Relative density of the glass is about 2.6. Modulus of elasticity 70 to 80 gigapascals, tensile strength 2 to 4 gigapascals and elongation or failure strain would be 2 to 3.5%. Carbon fiber, there are many types of carbon fibers here. These are the properties for the high strength carbon fiber. The fiber would have about 9 to 10 microns in diameter. Relative density is 1.9, 230 gigapascal modulus of elasticity. You see there is a big difference between the stiffness of the carbon fiber and the glass fiber. This is one of the distinguishing factors which could influence a decision whether carbon fiber should be used or glass fiber should be used. Where you want more stiffness of the composite, you would go for a carbon fiber because clearly you have a much higher modulus of elasticity. The tensile strength of the carbon fiber is about 2.6 gigapascal, again much higher than most of the composites that we will be reinforcing these materials with. Elongation at failure is less than in glass, it is about 1%, and in glass we had 2 to 3.5%. This again is another differentiating factor. Glass fibers could give more elongation in the composite, more ductility in the composite, whereas we will get much higher stiffness with the carbon fiber. Aramid fibers, as I said, are not very commonly used. These fibers, Kevlar is a commercial name, could have a diameter of about 10 microns, relative density of about 1.5 and modulus of elasticity ranging 65 to 133 gigapascals. Tensile strength is 3.6 gigapascals and elongation also varies from about 2 to 4. And remember that aramid is a polymer that is crystalline, that is why we have such high stiffness and strength. There are other fibers also, but we do not use them very much. Asbestos is now being phased out because it can cause health problems. Fibrillated polypropylene is used in concrete as a reinforcement, but not in the FRP, same as in steel. Steel fibers are used a lot in fiber reinforced concrete, we will talk about it later. Then we have other fibers also which are polymer based like nylon, cellulose, acrylic, polyethylene. Some natural fibers, wood fibers have also been used in some composites. Sisal is again a natural fiber. However, the composites that we use in strengthening and retrofitting applications are basically reinforced with glass or high strength carbon fibers, and to a limited extent with aramid. What happens to these fibers in the long term? In terms of chemical attack, carbon and aramid fibers exhibit good performance. They are not easily attacked by most chemicals. Glass fibers can, however, be damaged in alkaline media. We should ensure that the proper type of glass is used, which does not have a propensity of deteriorating in an alkaline media, in an alkaline environment. Ultraviolet light can affect polymers. However, carbon and glass fibers are not affected. Aramid fibers, again aramid being a polymer, can lose color and strength under consistent exposure to ultraviolet rays. In terms of heat and fire, what happens? The fibers generally maintain the mechanical properties until a certain temperature. This temperature, limiting temperature, is highest for glass fibers. Up to 1000 degrees Celsius you do not have a major change. With carbon up to 650 degrees Celsius you do not have any change. Aramid is lower, again remember this is a polymer fiber. So, the best performance is given by glass, followed by carbon, if in case you have fire or high temperatures in the application. This is also important because when we are strengthening a structure, this composite is generally on the exterior, on the outside surface of the concrete element or whichever element we are reinforcing. So, if there is a fire, there is a high probability that the temperature of the composite increases, and if this temperature is low or the fibers lose their mechanical properties very quickly, then the building will become unsafe before it is evacuated. So, the high temperature limits or the limitations under high temperatures should be known and analyzed when we use a fiber reinforced polymer in strengthening applications. Let us look at some different types of fiber composites. How are the fiber composites put together? In terms of the production, you can have fiber tapes, a tape that could be stuck on a surface to reinforce, that would be made by basically diffusion bonding. Remember we had talked about diffusion in the movement of atoms and also in changes in the microstructure, where you have fibers embedded in a resin that is coming as a foil, pressed together possibly with some temperature, and you end up having a composite in terms of a tape which is used to reinforce then the structural system. You might also want the FRP to have a certain shape which is not just a flat surface. Here what could be done is die is made of the shape, giving the shape that the element should have, and using a roller or a pneumatic system with air giving pressure over a rubber laminate that is pressed against the FRP, or with a die, this shape is obtained in the FRP. This light blue here is the final FRP composite. So, if you have a surface that is not just flat and that has to be reinforced, then you would have to make a die like this, and this will end up giving you a FRP composite of this shape and sufficient stiffness now to be adhered to the surface that we have to strengthen or reinforce. We could also have circular sections that are needed. We could also have circular sections that are needed. In that case, one of the technologies that is used to create this pipe like system is filament winding, where we have a mandrel of the desired inner diameter of the pipe spinning, and then a tape is now wound around it, and after the polymerization occurs you will have a pipe shaped element that can be used to give the element that we want. If you remember, when we did the introductory lecture on on construction materials or structural materials, I showed you an application of a bridge with made with composites, and there the girders are basically carbon fiber pipes filled with lightweight concrete, and pipes such as those could be made in this way. We can also have extrusion and pultrusion. Pultrusion is where instead of the material being pushed out, it is pulled out. Here you see the pulling force, and this is called pultrusion, but it is similar in concept to extrusion. So what we have is a die which is giving the shape or the cross section that is required, and then the element is cured before we get the final composite. Before it goes into the die, there is a resin bath which is giving the matrix. The fibers go through these resin, go through this bath and are pulled through the die, giving it the proper shape. So you can have composites again with different shapes, not just flat elements, which can be obtained through pultrusion. We can have multi-layer composites, just like we saw in the case of plywood. Remember, in plywood we looked at plies being put one on top of the other to make up the thickness of the plywood, and we saw also that some cases there were cross plies. There were different angles in the grains, and that makes up the composite, or in that case plywood. A similar system is used here. You can have unidirectional composites like in the left here. These have all the fibers in the same direction, that is the 0 direction. So obviously with more fibers we will get more strength, more stiffness, and the strength and stiffness will be basically in the direction of the fibers, along this direction. That is where the highest tensile stiffness and the strength would be. Now in case you had to strengthen in other direction also, then we can have cross plies giving a quasi isotropic system. So overall, because of the different angles of the plies, in the sense that you have now fibers not only in this direction but also in other directions. This is the 90 degrees ply, this is in 45 degrees, this is in 45 degrees but the other way. So you can have a system of fiber layers making up a quasi isotropic system. Quasi isotropic because it is now having similar properties in two directions, or in all, it has similar properties in all directions in the plane of the composite. Even though in each layer the properties are different, together when we make up the composite we have a isotropic behavior in the plane of the composite. Now let us look a little bit more in detail in the fibers that are used. We have fiber sheets which could be unidirectional or bidirectional. Fiber sheets say of glass. Okay. How much, any idea of time? I have time. 18 minutes are left. 18 minutes தான் முடிஞ்சிருக்கா? Looks like I'll finish fast. Okay. So let's look at let's look a little bit in detail in the fibers that are used in the FRP applications. Generally, as I said, we have glass, carbon and aramid. The fiber sheets or filaments of the fibers are normally unidirectional, in some cases they could be bidirectional, and this is finally used to create a polymer laminate. The sheets are available as raw fibers, that is just the plain fibers all put together in a sheet, or it could be pre-impregnated, that is there is a polymer, a pre-polymer that is mixed such that it surrounds the fibers, and the polymerization is completed or curing is done on the site. So this makes it easier to make the composite at the site. So you can have just the fibers, or you can have the fibers embedded in a pre-impregnated system. The polymerization is not completed, it is going to be completed at the site. This is how a glass fiber sheet will look like. You have most of the fibers running in this way, but you have some fibers running perpendicular. Similarly, you have an aramid system here. This is in Kevlar. More common is the case of carbon fiber sheets. You see here the shiny carbon fibers all in one direction. Generally they are unidirectional. It would come in a roll like this, and when you spread out you have these shiny black fibers of carbon. When you want bidirectionality, remember when we talked about the plies, we said we will have fibers in different directions. Now these sheets have to be put in different directions to give bidirectional strengthening in the FRP. Now instead of using a sheet or a pre-impregnated system and you complete the polymerization or the building up of the composite at the site, you can use laminates, and I will show you some applications later on. So these are called prefabricated FRP laminates. They are fabricated by extrusion, where you push through a certain die the epoxy or the resin along with the carbon fibers. So you end up with a laminate with unidirectional carbon fibers. These again come in rolls such as this. So you see here a roll of laminate. When the laminates are stretched out, they are like this, with a tensile strength of about 2.5 gigapascal. Elongation is about 1.5 to 1.6%. Remember, now we have the properties now of the laminate, not just of the polymer. We have now the properties of the laminate, not just those of the polymer. So here you have a tensile strength of 2.5 gigapascal and elongation of about 1.5%. Now this laminate already has its polymer matrix polymerized. So this laminate just has to be stuck, glued or adhered onto the surface that we have to reinforce. The advantage of this is that we do not have to worry too much about whether the polymerization of the FRP is done properly or not in the site. There could be errors of due to the workmen that are not coming in when you use a laminate directly, but in some cases we cannot use laminates, we have to use sheets. Now what would be the tensile behavior of a laminate or a sheet that is polymerized? Here we have a sheet, a polymerized FRP sheet with strain gauges. The strain gauges are marked as 1 and 2, and this is going to be pulled. We are going to do a uniaxial tensile test, and this is the section. The view from the other side, you see a thin edge and you see the wires coming from the strain gauges. Now when we test FRPs with carbon and glass fibers, you will get typically behavior such as this. On the x axis we have the axial strains in microstrains, on the y axis we have the stress. You find that carbon fiber gives an FRP system with much higher stiffness. You see the slope here is much higher than in the case of glass fiber reinforced polymer. The slope is higher, so that means the stiffness is higher. The failure stress is also higher for carbon than for glass. This value is much higher than this. On the other hand, we find that at failure the glass fiber composite has a much higher strain than in the case of carbon fiber. So this gives us an indication where we would use carbon fibers and where we would use glass fibers. When you need higher stiffness and strength, carbon fibers are used, and when such high strength and stiffness are not really a requirement, but you need a lot of ductility, there is going to be more strains that the system is going to endure, then we can go for glass fibers. And remember, glass fibers are much cheaper than carbon fibers. So if you can get away with using glass fibers, that is of advantage to us. Here are some more quantitative values for properties for different systems. This is with glass, aramid and carbon embedded in epoxy. Fiber volumes in all the cases are about 0.6, that is 60% of the composite is made up of the fiber. We have now the longitudinal modulus, the Young's modulus along the direction of the main fibers, ranging in glass from 40 gigapascal to carbon fibers 140 gigapascal. Aramid has an intermediate value. This is the transverse modulus, that is in the direction perpendicular to the main fibers, and you see that since we are applying tension in the other direction, the fibers are not contributing or contribute very little, because you may have some systems with bidirectional fibers, but generally we find that there is a big difference between the transverse values and the longitudinal values. And this is the shear modulus, ranging from 2 in aramid to about 4 in the case of glass to about 7 gigapascal in the case of a carbon fiber reinforced epoxy. Other properties: Poisson's ratio is about 0.3 in all the cases. Longitudinal tensile strength, again you have in the lower range glass about 1000 to 1300 megapascals, much higher values in carbon FRP 2300 megapascals in this case. Compressive strength is not really critical, because you will not generally have these fibers acting purely in uniaxial compression. However, just to see the values, again we have at the lower end something like aramid and glass, and at the higher end we have carbon FRP. Now we saw that there is a difference in properties in the longitudinal direction along the axis of the fibers, along the direction of the fibers, and we had much less stiffness perpendicular to it, and this figure gives you an indication what really is happening, though it is obvious. In this case we have on the y axis the tensile strength, and on the x axis we have the angle between the fibers and the stress, and we see that if we pull along the direction of the fibers, we have a very high tensile strength, because this is the direction where the fibers are acting, and the fibers are those which have the highest stiffness and the strength, and not the polymer. However, if this angle changes and you go to 30 degrees, 45, 60 and finally 90, we see that the strength gradually decreases, because the fibers are less and less in the best possible direction. So as we go from the 0 degrees where the stress is along the fibers to perpendicular, we see a decrease in the tensile strength. So in the application that we are designing, we have to understand which would be the preferential direction of the fibers for that particular application. We have to see where are the tensile stresses coming, what are the directions that they are acting, imagine or decipher from that where the cracks would occur, and use the composite such that the fibers are along the direction such that the tensile stress is resisted and cracks do not open. Now let us see the different cases of strengthening of concrete structures using FRP. What would be the steps? It is not just adhering the FRP on the structure, but there are certain steps to be followed. First of all, there has to be a proper structural analysis and design, just like you would do reinforced concrete design or steel design. You have to now design the reinforced structure or the strengthened structure. So there has to be a proper structural analysis done, and the design basically telling you what is the thickness and what are the properties required of the FRP. Then we have to choose the appropriate composite. For example, whether we go for carbon fiber or we go for glass fiber, what would be the number of layers, and so on. Very importantly, the third step is the preparation of the base. We are going to adhere, we are going to stick the FRP onto a concrete surface. we know that the FRP is very strong, very stiff, and if the base is weak, the base will fail instead of the FRP failing or even reaching stresses close to failure. So the preparation of the base is very, very important. We cannot use FRP, we cannot use FRP on a base or surface that is very weak, dirty, or not well prepared. Finally, it is the application of the laminate or sheet. Here workmanship is very important. Unless the laminate or sheet is properly applied, we will not be able to transfer stresses, we will not be able to do the repair or strengthening as desired. Finally, there should be a quality check to check whether the bond has been achieved, whether there is a continuous adherence of the FRP on the concrete surface. So these are the different steps needed for getting proper strengthening of structures with FRP. So I talked to you about the base. To prepare the base, we should keep in mind that the base before the FRP is put on it should be clean, should be dry, firm, that is no loose particles, no weak areas. It should be rough enough so that the epoxy now bonds well. If it is very smooth like a polished surface, then the glue binding the FRP and the concrete will not have enough surface area to bond to, and you can have delamination. It should also be free of grease, any contaminants. So we should be very careful on even the people who are applying this FRP, they should not cause contamination to the surface, otherwise you sacrifice the strength that we will be able to get. Ideally a surface should be like that shown in this picture. You should be able to see a concrete surface without the paste layer. You should be able to see some sand and aggregate particles. So clearly you should expose the aggregates or the inner part of the concrete by removing the paste layer which is generally seen on the surface of concrete. The texture has to be slightly rough. Now this may be subjective, with experience a person would know how to make the surface rough enough. However, we can also use references of textures recommended by the International Concrete Repair Institute. So this ICRI has made surfaces and classified them which can be used for specification. There are notations given, for example CSP4 is light scarification, and the guidelines given by ICRI tells how this can be achieved, and even you have a certain surface that can be touched and seen if the same physical appearance is obtained in the site. Similarly, you have CSP5, this is medium short blasting, then CSP6 medium scarification, where you have you can easily see that the depth of the roughness is much higher than here. So that there are different ways of defining textures and even specifying textures, but generally what is done is based on the experience the workman would know what is the level of roughness that is required for a certain FRP system. Before a surface can be used, all cracks should be filled up. So any cracks, this would be say the top of a bridge deck, all cracks, if this is going to be reinforced with FRP, should be filled up. You cannot have a discontinuity on the surface, otherwise there will be a stress concentration at the crack and there will be a delamination starting off from the crack along the adhesive between the concrete and the FRP. So all cracks should be filled up, they should be injected with an appropriate resin or other material, such that when you bond the FRP, you are bonding over a uniform plane surface and not a cracked surface. This is a picture showing how the bottom of a slab is being prepared. You have an abrasive disc that is being used to remove the cement paste layer that you see here. Here you do not see it because this is the treated surface or the prepared surface. After abrasion we are starting to see some sand and aggregate pieces. So, cleaning by abrasion is often used to prepare the concrete surface. The FRP should be cleaned so that there is no grease or contaminants on the FRP laminate that could harm the adhesive or the nature of binding that we will get. Then epoxy is applied to the concrete surface. So, this is the concrete surface with the epoxy. These pieces of steel that you see here are to hold the FRP in place until the epoxy cures and becomes strong enough to support the FRP. Otherwise, by its self weight, say this is a surface that is the bottom of a slab, by the weight of the FRP can fall off because the epoxy initially does not have much strength. So, after the FRP is placed, these steel pieces are used to hold the FRP in place, so that during the polymerization, during the curing of the epoxy, there is no debonding of the laminate. Locally, there is some pressure which has to be applied to make sure that the FRP sticks well, and also to remove any air or excess epoxy between the FRP and the concrete. And such type of systems can be used in all surfaces. Here you see pictures from a retrofitting of a tunnel. Say you had a tunnel with cracks running longitudinally along the tunnel, a system like this could be used to reinforce. These are now the FRP laminates. You see that very few people are involved because the FRP is very light, even the scaffolding is a light system. If this had to be done with something else, say concrete or steel, you would need a lot of equipment, lot of people involved because of the weights involved. Here the FRP is handled, you see in the picture there are just 3 people handling the FRP. The FRP now is put on the curved surface, adhered and held in place like what we saw in the previous pictures, and after the epoxy is cured, we can even coat the whole surface with a protective paint that would protect the FRP and the glue from contamination, and also maybe give a good aesthetic appearance. In some cases, after the FRP is applied and the surface is painted, we would not even notice that the surface has been reinforced. So, I will finish this part of this lecture with looking at the advantages and disadvantages, that some of which have been discussed. Advantages clearly of FRP, we see that it is lightweight because of the low density of the polymers and the fibers, much lighter in weight than other alternatives like concrete and steel. It is adaptable to curved surfaces because these are thin laminates or sheets that can be put on any shape that we want. The application is also fast. Some epoxies can even cure in a few hours. So, the application could be quite fast and little interference with the normal use of the structure. Say we have to repair a bridge, we cannot close down the bridge for many days. So, the application can be quite fast. So, the main advantages of FRP are lightweight, it is adaptable to curved surfaces, and we have applications that can be very fast. However, we also have some disadvantages or difficulties. One of it is that we have brittle failure. We saw in the case of the tensile test that we have linear behavior and then we had sudden failure. So, there could be a brittle failure. So, we have to ensure that the failure stress of the FRP is never reached in an application, otherwise you will have a sudden brittle failure. Anchorage is difficult, we will talk about it little bit more in the second part of this lecture. If the FRP is not properly anchored to the concrete surface or any other surface that we are reinforcing, the FRP will peel off, there will be a delamination starting from the ends and we will not be able to exploit completely the strength of the FRP. Cost is still quite high, even though now with more demand and better systems coming in, the cost is coming down, cost is still reasonably high. The other disadvantage is we do not have a lot of design codes and there is limited experience, though this is again building up and we have more and more applications being done and workers being trained on how to apply FRP in applications. This is a limitation, and until there is wider practice and design codes coming up, we will have a certain disadvantage in terms of usage of FRP. So, we looked at different systems that can be used for strengthening and retrofitting. In the second part of this lecture, we look at some case studies, and I will show you some typical cases that where FRP has been used for strengthening and retrofitting, and I will tell you which are the type of FRP that was used and how it was applied to the concrete surface. Thank you.